In exercise 1, we're told that the cost of airing a commercial on television is modeled by the function c of n equals 110n plus 900. N is the number of times that the commercial is aired. We want to know, based on this model, which statement is true. Here's our function. We're told that n is the number of times that the commercial is aired. 110, therefore, must be the cost to air the commercial, because it's 110 per n. 900 is a fixed amount. That's the cost to produce the commercial. And so read the choices carefully. We see that choice 3 is the answer. In exercise 2, we're given a graph. It represents a jogger's speed during a 20-minute jog around a neighborhood. Which statement best describes what the jogger was doing during the 9 to 12-minute interval of her jog? Let's take a look at the graph. We're looking from 9 to 12 minutes, and so this is the part of the graph that we're interested in. On the x-axis is the amount of time, and on the y-axis is the speed that she was running. 9 minutes in, she was running at a rate of 6 miles per hour. 10 minutes in, she was running at a rate of 6 miles per hour. 11 minutes in, the output is, again, 6 miles per hour. 12 minutes, again, 6 miles per hour. So it looks like from 9 to 12 minutes, during each of those times, she was running at a rate of 6 miles per hour. Let's look at the choices. Read carefully. Choice 4 is our answer. She was jogging at a constant rate. In exercise 3, we're told the area of a rectangle is expressed as x to the fourth minus 9y squared. The product of the length and width of the rectangle could be represented as which of these expressions? We notice by looking at the expression that we want the area, length times width. We can take that original expression and factor it. Notice that what we have is a difference of two perfect squares. X to the fourth is a perfect square, and 9y squared is a perfect square. They're connected by subtraction. When we have a difference of two perfect squares, a squared minus b squared, it factors into a conjugate pair, a plus b times a minus b. The a value is x squared. The b value is 3y. We can factor this expression, therefore, into x squared plus 3y times x squared minus 3y. Look at the choices carefully and determine which matches this expression. Choice 2. Suppose you weren't sure how to factor that expression. You could take a longer approach. You could take each of the given choices and multiply them out. See which pair gives you x to the fourth minus 9y squared. When we do that, we see that we get that product when we multiply the binomials in choice 2. Again, choice 2 is our answer. In exercise 4, we're given 4 tables. We're asked which table represents a function. Remember, when we have a function, it means we have a relation where each input has only one output. We can do this a few different ways. We could consider what the tables would look like if we were to write them using a mapping diagram. Notice choice 1, the input 2, has 2 different outputs. Same is true with input 4, 2 different outputs. This is not a function. In choice 2, notice that the input 0 has 2 different outputs. Also, the input 1 has 2 different outputs. This relation is not a function. In choice 3, notice that each input has one output. 3 produces a 2, 5 produces a 4, 7 produces a 2, 9 produces a 4. A function is completely predictable, and each input here has exactly one output. This is a function. Let's check the 4th choice. We see that the input 0 has 2 different outputs. Choice 4 is not a function. Therefore, choice 3 is our answer. Another option for solving this problem would be to look at the graph of each table. Remember, for something to be a function, it has to pass the vertical line test. The vertical line test shows us if each input has only one output. Notice that graph 1 fails the vertical line test. Graph 2 also fails the vertical line test. Graph 4 similarly fails the vertical line test. They each fail where the blinking red line is. However, choice 3 passes the vertical line test, and therefore, again, choice 3 is a function. Choice 3 is the answer. In exercise 5, we're given a graph of an inequality, and we're asked which inequality is represented in the graph. Remember, the equation of a line is y equals mx plus b. M is the slope, b is the y-intercept. Let's look at the graph. We see that the slope is -3. Take a point on the graph to get to the next point, down 3, right 1. The y-intercept is 4. And so we could write the equation of the line y equals -3x plus 4. Look at the choices carefully, and we can see that choice 3 and choice 4 are clearly not correct, as they have the wrong slope and the wrong y-intercept. What about choices 1 or 2? How can we determine between them? Remember, if we're shading above the line, it's greater than or greater than and equal to. If we shade below the line, it's less than or equal to. Take a look at our graph. We've shaded above the line, which means we're in the greater than or equal to. Which one is it? We see that we have a solid line, which means the points on the line are included, so greater than or equal to is correct. The equation of the inequality is y is greater than or equal to -3x plus 4, and so choice 1 is our answer. In exercise 6, we're told that a farm stand stole a total of 165 pounds of apples and peaches. They sold apples for $1.75 per pound and peaches for $2.50 per pound. They made $337.50, and we want to know how many pounds of peaches they sold. In this problem, I see two different pieces of information: the fact that they sold 165 pounds of fruit and the fact that they made $337.50. I can write two different equations from this information, and so a system of equations is a great way to go. Let's define our variables. A is the pounds of apples, P is the pounds of peaches. Apples were $1.75 per pound, and peaches were $2.50 per pound. Now let's take the information and see if we can write some equations. We had 165 pounds total and $337.50 in total sales. The number of apples plus the number of peaches, and by number I mean the number of pounds, was 165. So A plus P is 165. The total was $337.50, $1.75 per pound of apples, 1.75A, plus $2.50 per pound of peaches, 2.50P, equals $337.50. Now I have a system of equations, and you can solve this using any of the methods you know for solving a system of equations: elimination, substitution, or graphing. If I'm going to use elimination, I need an opposite variable, and so I'll multiply the first equation by -1.75. Now, when I distribute that, I have opposite variables for A. I can solve the resulting system, add the equations together, and solve for P. P equals 65. The fruit stand sold 65 pounds of peaches. Choice 3. You could also use a different method for solving this system. You could go ahead and you could use the method of substitution. Take one of the equations and solve for a variable. For example, A plus P equals 165. Solve for A, and then substitute that into the other equation in place of A. Solve the resulting equation, and once again, P equals 65. 65 pounds of peaches. Choice 3. In exercise 7, we learn that Morgan is a wrestler. Morgan can start wrestling at age 5 in Division 1. He remains in that division until his next odd birthday, which means when he becomes 7, he moves up to Division 2. We want to know which graph correctly represents this information. Let's begin by organizing what we know. From ages 5 to 7, Morgan's in Division 1. Birthday comes, 7 to 9, Division 2. 9th birthday comes, it's an odd birthday. He's now in Division 3, stays in Division 3 from 9 to 11 years old. 11 to 13, division 4. 13 to 15, division 5. Now let's look at this a little more carefully. At age 5, Morgan is in division 1, but as soon as he turns 7, he moves to division 2. Written as a mathematical inequality, we would include 5, but not include 7. 7 would move him to division 2. We can look at each of these intervals and set up the intervals to get an idea where our open circle and closed circles will be on the graph. Then we can compare to the graph. On the first choice, we see that age 5, he's in division 1, and he remains in division 1 up until age 7. At age 7, he moves to division 2. Notice there's an open circle for division 1 at age 7 and a closed circle for division 2 at age 7, which indicates that once he turns 7, he moved to the next division. We see a similar change when he turns 9. When he turns 9, he moves to division 3. Open circle at 2 because he's not in division 2 anymore. Closed circle at 3 because he's now in division 3. Same thing is true for 11, and the same thing is true for 13. Choice 1 looks like a good answer. Let's check out the other graphs. Let's look at choice 3. At 5 years old, Morgan is in division 1. That sounds correct. But look what happens at 7. There are 2 closed circles on that graph, which suggests that Morgan is in both division 1 and division 2 when he turns 7 years old. That doesn't make any sense. Same thing at age of 9, age of 11, age of 13. Choice 3 certainly doesn't seem correct. How about choice 2? Choice 2 shows an open circle at 5 years old, meaning at 5, Morgan is in no division at all. At 7 years old, it shows that Morgan is still in division 1. We know he should be in division 2 at this point, but there's an open circle at division 2, which means that change hasn't happened. Graph number 2 doesn't make sense, and so that's not a valuable solution. How about choice 4? Choice 4 shows the same oddity at age 5, open circle, meaning Morgan's age 5 and is not in any division. Look at the next birthday, age 7, 2 open circles. Morgan is in no division at age 7. That doesn't make sense. We see that happens again at 9, 11, and 13. Graph 4 doesn't make any sense. And so choice 1 is our answer.